So my nick is Beched. Actually, the proper pronunciation is Beched. I do application security assessment and penetration testing at Inc. Security, and also compete in CTF competitions, hack quests, and other contests with r.org team. We'll talk about rapid application security assessment. So, what's the problem? There are several common situations when you need to test application as fast as you can. The first situation is pen testing a huge scope of IP addresses, or even one IP address which is full of web interfaces. And you've got, let's say a week to pen test 100 sites. So what should you do? You cannot properly pen test all of them because it requires a lot of time. The second case is bug bounty. Here you've got unlimited time actually, but if you stay for a week without doing anything, then all sweet and good accesses will be found by other people who are faster than you. And it will require you much more time to find more interesting bugs which are more complex than simple bugs. Another case which occurs quite often for me is estimating the cost of penetration testing, for example. The customer gives you a URL and you need to know how much does it cost to pen test it. Maybe it's one static page and you have nothing to do with it, or maybe it is huge enterprise application with a lot of interfaces, so it will take weeks to fuzz all the input points and find all the bugs. And the last common situation is CTF, when you should be very fast and you should solve the problem, the task, to get bonus points and to focus on the other next tasks. What's the solution? Here are random words about the solution of these problems, and actually, yes, it helps. You should prioritize your actions. What should you do first? What should you do last? You should parallelize them, and you should automate as much as you can. What about manual testing of big scope or rapid manual testing? There are many articles, presentations, and books on methodology of application testing, and they cover a lot of techniques, but yeah, the manual testing is good because you'll not, for example, crash the application by hitting some link which says, for example, delete all the news, or you hit or 1 equals 1 into some input parameter and it gets into drop SQL query and you drop the whole table instead of exploiting SQL injection. Also, within manual testing, you can check for logical vulnerabilities, which are very hard to find with scanners. So, actually, you can capture some bugs within the limited time doing it manually. But if you've got many applications to test, it's much more difficult. Thus, even though automatic scanning sucks, you should do it, and you should focus on improving your tools. Semi-automated automated testing means that you launch each step and each action by hands, but each of these steps is performed by some tool. For example, you first launch Nmap, find web ports, web interfaces, then you launch Burp Suite Spider, and so on. This is very good and cool, and it suits very well for bug bounties. But again, if you've got a big scope, it doesn't work. Many pen testers that work several years in this industry develop their own dirty tools to do one or another thing. Generally, creating a solid application vulnerability scanner is a very complex task, and it requires even some rocket science because there are many algorithmical problems. For example, there are technical problems like crawling rich Web 2.0 applications and understanding the logic of the application. For example, the simple scanner doesn't understand if some interface some interface shows, let's say, the news, or it is some login form. It just hits some fuzzing strings in all inputs that it finds. And you, as a human, understand what it is, and you can perform one or another action. You can prioritize them. We'll measure the speed and the rapidness of our testing, automated testing, by two variables. The first is the actual time within which the test is performed. It depends on CPU and memory usage, because the more the usage is, the more time your machine spends on it. Of course, you can scale it, but nevertheless, this is important variable. But it also heavily depends on how much network requests you do. And this parameter is often much more important, because you need to keep the number of connections with the web app low. You should be silent and do not make noise for IDS, IPS systems. Again, it decreases the time. If you make less requests, you generally spend less time. This is trade-off, because you need to decide what you need more: coverage, better coverage of all inputs, of all interfaces, or better speed. So actually, the topic of this talk should be not time less than t, but requests less than some q. Let's say we should make not more than 1,000 requests on each host. We'll observe several tricks that I use for this. Tricks are both in technical plane and algorithmic. First, technical view on this problem. There are several simple and well-known tricks which save us time. While scanning, you can use one connection for several requests, even for 20, 50, 100 requests, if you use a keep alive header. Also, when you are dear-busting an app, or you are testing for some time-based payloads, SQL injections, or, for example, SSRF vulnerabilities, or HTTP response splitting, then you only need the time and the response headers. That's why you can use just head method, not get or post. Well, post, you actually need post if you are fuzzing the post parameters. Then, if you crawl a site, it can take a lot of time. That's why you should first look at sitemap XML or robots.txt, or just Google the site, the domain, and find all the paths known to public. And you should not crawl these pages again. You can just process them, decide which of them are duplicate, and so on. Also, there are several tools like CMS map that get that have signatures for different CMS systems, and it guesses which CMS is installed on this particular host and which version is there. Then it can look up, it can look for this version of this CMS in exploit databases and say you if it is vulnerable or not. Login forms can be brute forced, obviously, with some very small top of passwords. Other technical issue is horizontal scaling. Not long ago, I saw this release by Yahoo. It's called Griffin and written in Go. It is a platform for distributing application scanning. You can write the modules for it, you can extend it, and it provides good horizontal scaling. You can deploy it on many servers and scan the app. I haven't used it actually, but I think it's a rather good idea. Now, much more interesting part, algorithmic view. The task is to increase the bugs we check in the same amount of requests. Task seems simple, but there are many issues with it. Let's remember what do we think and how do we think while we are testing the app manually. So maybe if you have ever tested a web app, you've seen such image in WebSuite when you've got a bunch of links to some interface which, for example, shows some article, and there is incrementing ID as a REST parameter, and simple scanner like a WebSuite scanner doesn't understand that it is the same page, even though there is a URL pattern obvious, and the contents of these pages is very similar content. Actually, this problem is not solvable generally, because you cannot exactly say if there is or there is no additional interface on some of these IDs. Maybe there are news on the first, there are articles on the first 1000 IDs, and in the 1337th ID there is admin panel with no auth. You cannot know this, but when you do it manually, you generally skip such checks and do not check each of these pages. You check just one. Common practice is to fuzz all of them when we are talking about automated scanning. In that Yahoo's Griffin project, uses a SIM hash algorithm described in this link. It was created for web crawlers and search engines, and is purposed for detecting the similar pages, obviously. The point is that it calculates a number for the page, or for the sequence, for any sequence. It can be a list of tokens, it can be a string, a list of chars, it can be whatever you like. And if the two sequences are similar in the common sense, then their hashes, their numbers will be close. Their distance will be low. So you can use this SIM hash algorithm to detect similar pages, but actually it can give false positives quite often, because the page can have a huge header full of some styles and scripts. It can have who's this? I don't know who's this. Okay. Who knows how to turn off an iPhone Whoa. So, false positives. Because of what? Because of header, because of footer, because of menu on the page. On the usually you've got a structure of web page where in the center of it you have got some content, and on the head, in the footer, and in the side panels there is some static content like menu. So such pages with such structure may be very similar, but anyway they are not the same. The logic behind them is different, so you should make low tolerance for sim-hash algorithm. Namely, you should detect the pages as duplicate only if the distance is very low, for example, 0. The next problem is gathering input points. Not the pages. Let's say we already collected the pages and filtered out the duplicate pages. Now we should gather the input points. Classical modern way of doing this is using some browser stack, for example, Phantom.js. Scanner plugs the URL in browser, hits all links, hits all forms, and sees where it got, what parameters are sent, what HTTP packets are sent. The quick and dirty way is just to parse forms, parse links with query strings, parse input parameters from forms here, and parse JavaScript containing some XML HTTP request parameters. But the interesting part is gathering unknown input points. Let's say there is some input parameter that is seen from administrative panel or not seen from anywhere, and you are testing an app without administrative account, and you cannot gather this parameter without having it on any web page. Then you can find it anyway by by iterative binary search. Yeah. So what is it? You take a big list of common parameter names collected from different CMSs, different engines, for example, page, ID, etc. And you construct a big query string of these parameters. For example, ID equals 1 and ampersand, page equals 1 and etc. All these parameters. You plug it into query string, you request this page and see if it changed. If it changed, then probably there is some parameter within this bunch which influences on the page in one or another way. You split the set into two subsets, plug each of them separately and see if something changes. You iterate like this and get parameters that influence page. But of course you should cut dynamic contents. For example, there can be some ads that have different size. So each time you request a page, it will have a different size and different content, and you'll get false positives. Now you've got input points, you've got pages, and you need to fuzz them. If we talk about burp suite, there are several modes of intruder. There is such a tool, intruder, in the burp, which allows us to fuzz the input parameters. And there are several modes of it, but generally the long way, the classical way, is to hit all the parameters with all the fuzzing strings containing some strings triggering one. But the clever way, which is used also in scanners too, is using polyglot payloads. By using them, you can check several vulnerabilities at once in one request. Here is the link to a rather good presentation about polyglot payloads. Why can they be constructed? How that can be done? Well, this is what I use sometimes. You plug a tag, then if you see a tag on the page, then it's XSS. You plug a carriage return byte, and you can see if there is response splitting. You plug quote, double quote, backslash, and check for bounds like SQL injection. Obviously, backslash should be put in the last position, as well as null byte. The payload below is for PostgreSQL and MySQL. The point is that in MySQL, the hash byte, the hash symbol, means comment. All after this symbol should be ignored. And in PostgreSQL, this symbol is XOR. And also in MySQL, the construction /* means that this part of query should be executed only in MySQL, not in others. PostgreSQL interprets this as a comment. Now, we've done all of this, and what about the question of estimating the cost of penetration testing of web app? What we actually do when we look at the web app, I receive a URL and guess, would I hack it in one day or I won't? I'll take a look at it for 5 minutes and say, yeah, it should be hackable, or maybe not, it will be hard, it will take a week, or possibly it will not be hacked. There are some heuristic, and why not automating them? Why not automating the thinking? I think it's rather easy. The thinking flow is like this. Look, it's an enterprise.NET site written by professionals with good user interface and clear code with CSRF tokens and etc. Probably it will not be hacked. Or it is some default CMS installed, for example, WordPress. There are no plugins, so if I don't find 0 day in WordPress, I won't hack it. Probably. And another situation when you see custom written PHP shitty code full of mistakes, full of incorrect user interface, incorrect HTML, invalid, and you guess that probably you'll hack it fast. Let's point out some features, some metrics, which allow us to detect the hackableness of the site. Let's say it's platform, the programming language in which the app is written, the web server software, the engine which was detected, the CMS or a framework, for example. The number of input parameters which were parsed from the main page. I mean, from the links. When you see a query string with a lot of parameters, then you see that you've got something to fuzz. The number of script tags, the number of inputs, and whether or not site works on HTTPS. Well, the simplest first check which I perform is detecting whether the app is PHP app or not. If it is PHP app, then probably it is hackable. If not, well, maybe there are some client-side vulnerabilities, but generally it's much less hackable. But actually, if we want to automate this really and get more rigorous detection, you should do, for example, machine learning. Here is the actual decision tree for detecting, for deciding whether app is hackable or not. I built it today when I scanned several hundred sites with my data script and collected the features that we mentioned above. Actually, that simplest classifier about PHP was not that wrong, because this rigorous algorithm showed that if the app is written in PHP and there are at least 4 get parameters on the main page, and there is at least one script tag, then it's vulnerable. At least in all the sites I've scanned, this property holds. So you can make just one request to the page, measure the features, then plug them into this decision tree, traverse it, and get the result. The top of it is the server, I guess. So it's like there are many questions. If it is a patch or not. If it is, then you go to the right. If it is not, then you go to the left. And in the leaves of this tree, there is an answer. The next problem is the following. When you scan a site, for example, with Burp Suite or Akinetics or any other scanner, it aims better coverage, which means that it scans everything it sees. Every URL should be scanned. It builds a queue of URLs and fuzz each of them. But when you've got only, let's say, 1,000 requests for each site, there's no good scanning each image for vulnerabilities. There are no vulnerabilities in images generally. That's why you should somehow sort the queue in order to get better coverage in the limited number of requests. We'll calculate the priority of each page and build a priority queue. It's a data structure like queue, but it is sorted by priority. So when you pop a value from this queue, you get the value with lowest or highest priority. It's equivalent. Which features should we calculate? I used rather obvious features like like whether we detected a platform or not. If we didn't detect in which language the page is written, then the platform is none. If we detect it, then the platform is ASP, PHP, Ruby, Python, Perl, and etc. Another feature is content type returned in HTTP headers. If it is static content type, then probably there are less vulnerabilities in this interface. Well, there can be vulnerabilities, but we make the priority lower. The response code, if this page is a not found page, there's no sense fuzzing it a lot. Let's take it to the bottom of queue. And a bit of natural language processing will detect if there are some words, let's say stop words in a URL containing the words like account, admin, password, etc. If the page if the path contains such words, then possibly this is important page, and you should fuzz it first. This is the code that calculates such priority. It is rather guessing formula, which I guessed. So if you do this, then you see something like this. I'm scanning r.org forum here. As you can see, show thread.php path has the lowest priority. It means that it has highest priority. It will be scanned first. And all the PHP files have better priority. Not all, but actually. But most of them have better priority than JS or PNG files. And this makes sense. This is good. And these pages have different priority because, for example, show thread PHP has parameters, input parameters. It has more input parameters. That's why the priority is higher, lower. Well, in sense, it's higher because we've got more things to fuzz. This all was about black box. But in the description of the talk, I wrote Whitebox, even though I don't know anything about science of static analysis, static code analysis. But anyway, I'll say a couple of words. Static code analysis is much more complex task, and it requires some science because you need to do model logics, you need to parse grammar and build control flow graphs, etc. But anyway, even though many guys do this rocket science and write their scanners, they are not that good actually. They are good for large enterprise apps, for internal testing, for SDLC and other buzzwords, but when you need to hack fast, maybe they'll give you not much information and they'll run for ages. They'll require gigabytes of memory, etc. And actually, another point is that often ads, the samples which that marketing departments of the developers of such scanners give are constructed by people. I mean, people took some vulnerable code snippet, found their vulnerabilities by hand, and then implemented them in the scanner to show to customers that their scanner can find these bugs. Well, okay. So that's why we should have some dirty hacks and regexps for semi-automating our work. When we look at code snippets with our eyes, testing them by hands, string by string. What I do, especially for CTF competitions, when you've got a small amount of code and should analyze it very fast, I do grep, obviously, but it's not the simple grep. It's a bit better grep. Let's collect dangerous things for each language. Let's say in PHP it's MySQL query, eval, include, require, read file, etc. These are dangerous functions. You should not trust user input and plug it into these functions. And let's generate regular expressions which will find the occurrences of such functions followed by anything not containing a securing function. Let's say if it is MySQL query, then there should not be something like int_val or MySQL real escape after that. And then followed by variable. Maybe variable from super global array like get or post. If we generate such regexps, we can spot out dangerous bottlenecks in the code very fast, and then analyze them by hand. For example, we can write a plugin for IDE, which will find such things. Then you can find the usages, find the declaration of this part of code, and trace from where you can get to this sync. Is there any user input which gets there? This can be done by hand after you spotted out these dangerous places. And this helps a lot when you have 5 minutes to do something very fast. It's, as I already said, especially needed for competitions. So, summary. Should I read this loud? Okay, so there are ways of solving the mentioned problems, and this can be done rather well. I think that no one actually built a good platform for rapid testing, because usually the aim of testing is better coverage, and you've got a lot of time. But such rapid methodology can be used, applied, for example, for massive monitoring of websites. For example, when I built today this decision tree, I took Alexa top rank, took some random part of it, some random interval, about 1,000 or 10,000 sites, and just scanned it with the limit of 1,000 requests with my data script. And got the features which I plugged into scikit-learn Python library, and learned it to decide whether the site is vulnerable or not. Some of reviewed techniques and scripts I'll post into my repository. They are not debugged yet, so they aren't there yet, but there is an old libpywebhack script there which does part of the work which I described here, without priority queue, sim hashes, and other cool things. So look at GitHub, write, hack, boom. That's all. Thanks.
Any questions? Okay, I have a question about decision tree and algorithmic view. So, at the end, what is it in the end? Is it something like plugin for burp, or simple script that takes some URL and output some decisions?
Well, I put a generation of Python code of decision procedure into, I implemented such a generation in my script. So it builds a decision tree with the help of scikit-learn library. Then it traverses this tree and builds if-else statements.
Did you try to integrate it into burp? Because
no, I wrote it yesterday, so I didn't
okay.
Try anything.
Because you know, burp has Python Python opportunity to plugin to write plugins.
It has, but I think it's rather slow. But for this purpose, it suits, I think, because we should make only 1 or 2 requests. We'll make 1 request, get the headers, the contents, calculate the features, and output.
I ask it because you show us examples from burp, and it's really often a situation when you look on burp and say, oh, there's only 20% of scanning, but I need faster or something like that. By the way, as I remember, burp also tried to resolve this problem by showing you some kind of dialogue and ask you to do you really want to scan these URLs or something like that? But it's very difficult to understand. Do I really need it to scan it or not? So such library, I think it will be really useful for integration into such solution like burp.
Yeah, the dialogue is bad because it's not automated, and if you've got 1,000 URLs, you should look at each of them and remove
some
it.
Kind of checkbox here there, and yes, it's not very convenient.
Yeah, I don't know the internals of burp, but I think maybe priority queue can be implemented inside of it.
It's written in Java, but it has
API.
API, yes. For example, for Python, for Java implementation of Python code.
JSON, yeah.
Yep, JSON. So, any questions?
Hello, very interesting talk. I don't want to start trolling about burp and OSZap, but I don't know if you know about this great tool, and it has Python support too and JavaScript. So do you think maybe you can try to work with us to try to implement it or trying to test it on a OS open. You can go into the code wherever you want, not like some other apps.
Yeah, as I already said, I was coding this yesterday, so I had no time to integrate it in something else. So I've got only my scripts with my bugs.
Okay, so you have opportunity to integrate it into all tools
Yeah.
at this night. Okay, any questions? So if you have written it yesterday, so I can ask you about how many sites do you already test with this methodology?
A couple of tens of thousands.
From Alejo top 10.
Well, while I was debugging the scripts, I tested about a couple of tens of thousands.